In this session, we will learn about or we will discuss about the principle of virtual work. This is one of the most fundamental concepts in mechanics or in analysis, and this is extremely powerful in considering a large number of problems that arise in mechanics. Okay. So basically, from the basic physics definitions, we know that work is the dot product of the force and the displacement. Right. So work is a scalar quantity where we take a dot product of two vectors, the force vector and the displacement vector. And if we are talking about a body in general, as shown here, uh, F in general is the resultant force vector, which means it is the vector sum of all the forces acting on a body, and D is the displacement vector that that body undergoes. Now, if a body is in static equilibrium, that will indicate that this summation of all the forces on the body must be zero, right? So that is the definition of a body being in static equilibrium. So that means this resultant force vector F will be zero. Now, what it implies is that for a body in equilibrium, if we apply, let's say, an imaginary displacement or a virtual displacement, which we are calling by vector delta, then the virtual work done by the forces will be always zero for any delta, because this the force field acting on the body is in static equilibrium. Now it is possible that because of this acting force field, there is a displacement which is, let's say, the real displacement, which is a consequence of F or of these forces which are acting on it. So this body may have some real displacement also, but here we are essentially interested that let's say this body is under static equilibrium under the forces, which means this resultant force vector F is zero. Then by definition of the work, if we were to apply or if we were to displace this body virtually or in an imaginary world, if we assume that this body undergoes certain amount of deflection, for all such deflections or for all such virtual displacements, the virtual work will always remain zero. Okay, because it is a dot product between F and delta, and since F is always zero, so the virtual work is always going to be zero. Okay. Now, of course, there needs to be some requirements for delta. One is that it should be small. Okay. So it should be small enough so that the positioning of the forces which are under equilibrium does not change, which means that the forces which were in equilibrium earlier, they remain in equilibrium after the virtual displacement. And second is it should be compatible with the geometry of the structure. Okay. So let's say if there was a beam, and let's say this beam had a load P, real force P, because of which there was some deflection. Now if we apply, now let's say this is delta, the real displacement. Now if we were to apply a virtual displacement to this beam, let's say this is small delta, which is virtual. So at the support, where geometrically the beam is required to remain stationary, or it is required to have zero deflection and zero slope, this virtual displacement field have to necessarily respect that, right? So we cannot choose any delta or any virtual displacement. The virtual displacement should be compatible with the geometry or the end conditions of the system. Okay. So with these this few background, we reach the statement of the principle of virtual work, or PVW. And in this case, since we are applying virtual displacements to a system which is already in equilibrium, we also sometimes call it the principle of virtual displacements, or PVD. Okay. So the statement goes like this, that given a real force field and a virtual displacement field, right? So the virtual work done by the force field is zero if and only if the force field is in static equilibrium. So this is a both-way implication. Okay, what it means is that if the real force field is in static equilibrium, the virtual displacement under any admissible or compatible virtual displacement will be 0. And vice versa, if the virtual work done by the force field is 0 under a displacement or under a virtual displacement, that force field is going to be in static equilibrium. Now this is a very powerful statement, and it can be used in a variety of ways in mechanics problems. So in this session we will see how this can be used to find support reactions. So I believe you would be already aware of application of the static equilibrium equations directly to find the support reactions. So in this case, let us see how to apply PVD, or the principle of virtual displacements, in finding out support reactions. Okay, so this is a simple 4-step process. So first we consider the structure as rigid, okay, which means so just like in the beam here we considered a bending type of deflection. So here for finding support reactions we will assume that it is rigid, which means it cannot deform, it can only move. Okay. Second is that we remove the support where the reaction is to be found, right? So this is customary. So where as long as the support is there, that force will not be revealed. So when we remove the support, that force gets revealed. Then we apply a compatible virtual displacement to the system, and then we apply the principle of virtual displacements to find the reactions. Let us see this through a very simple example. So let's say we are given this simply supported beam, and we have to find reaction at the support B. Okay. So first step is we remove this support. We have to find the vertical reaction at B, so we remove this support, right? So after removing the support at B, the force VB comes into play, so that gets revealed. This P is the real applied force, and this VB is the real reaction due to that applied force. And now wherever this force or the unknown force is acting, we apply a virtual displacement. Let's say in this case to this particular beam, assuming considering it as rigid, we will apply a virtual displacement. So we lift it up, so basically it becomes like that, right? So at the end B, we apply an upward delta, which is the applied virtual displacement. Okay, and of course because of this applied virtual displacement delta, there will be an induced virtual displacement at the location of the force P, and let's call it delta 1. So delta is the applied virtual displacement, and notice that this applied virtual displacement is ensuring compatibility with the ends or the geometry, right? So at the end A, this beam cannot translate. It can rotate, but it cannot translate because that is a hinged end. So after application of the force of the displacement delta, the deflected shape of the beam becomes like this. It remains a straight line because we are considering the body as rigid. It cannot bend. Okay. So delta is the applied virtual displacement, and delta 1 is the displacement induced at the location of P. And now delta 1 can be computed just by geometry. So this is these are two similar triangles, right? So delta 1 by A, and delta by L, that ratio would be same. So delta 1 comes out to delta times A by L. And now we write the statement for principle of virtual work. So for the force P, the displacement is happening in the opposite direction of its application. So delta 1 is happening upwards, whereas force P is acting downwards. So that dot product will be P times delta 1, so P times delta A by L, plus at the location of B, the force is in the upward direction and the delta is also in the upward direction. And hence the work done, or the virtual work done by VB, is VB times delta, right? And there is no other force acting as of now. So this is the overall force displacement dot product. So basically here this delta would cancel out and we would get VB to be PA by L. And this is something which you can easily recall from direct application of the static equilibrium equations also, right? Let's look at another example where, let's say, this cantilevered beam is given and we have to find the moment at joint A, or at the support A. So the first step is we remove or we release the moment here. So basically this fixed support becomes a pinned support, right? So fixed support will restrain translation in X, Y and rotation, all three. Whereas now we need to release this rotation part. So we make it a hinged support, and then that reveals the moment at A, MA. And this force at B acts as it is acting. Now at the location of MA, we apply a virtual rotation. Okay, so we apply a virtual rotation at the location at A, and this virtual rotation again, after respecting that this body has to be rigid and that here it cannot translate. So when you apply a virtual rotation, it will deform like that. So basically this beam goes upwards, and at the location where P is applied, there is delta 1, which is an induced displacement at B. Okay, and since theta is small, by definition theta needs to be small, so delta 1 can be written as just theta times L. Okay, and now we can apply the principle of virtual displacement. So the work done by the moment is plus ma times theta, because both the rotation, applied virtual rotation, and the moment assumed direction are the same. And then here P is acting downwards, whereas delta 1 is happening upwards. So we have minus P times delta 1, or minus P times theta L equal to 0. And now there is no other force or moment acting which can do work. So again theta will get cancelled out, and we get MA is equal to PL. So this is the moment at A. Now we may also ask how to use this to find vertical reaction at A. Okay, so now we need to allow the vertical movement of the joint A, right? So that becomes like a guided roller support. So basically this will restrain the horizontal movement, and this will restrain the rotational movement, but now this will allow the vertical movement. So after this support gets converted to a guided roller, we reveal a force VA, which is the vertical reaction at A, to be found. And next step is that at A we apply a virtual displacement of delta upwards. Okay, now the direction we can assume upward or downward, the signs will take care of them, take care of these assumptions. And because this beam is rigid and this beam cannot rotate at A, or it cannot translate in the x direction at A, so this entire beam will go up, right? So the induced virtual displacement delta 1 at the point B will be equal to delta. Okay, so now again we can write the principle of virtual work. So the work done by reaction at A is positive because delta and VA are in the same direction, and work done at point B is negative because P is acting downwards, delta 1 is acting upwards. So again delta gets cancelled out, and what we get is VA is equal to P as the answer. Let's look at a little bit more complicated problem. So let's say this this sort of propped cantilever beam with an internal hinge at B is given with the dimensions shown, and we have to find all the reactions. Now if we have now let's first look at, if we have to find MA, we need to convert this support A into a hinge support, right? So here we convert it to a hinge, and then we apply a virtual rotation at A, which is theta A, right? So remember that all the intermediate spans of the beam will remain rigid because we have assumed it to be so. And this theta A, the deformations it causes have to respect the boundary conditions or the support reactions, right? So from here it goes like that, and then B is an internal hinge, so the beam can rotate about it, and from here to D again it's a straight line. Okay, so now there are various moments and forces acting at different places. So at A, MA is the moment to be found, or the support moment, and theta A is the applied virtual rotation in the same direction. Okay, at the point E, there is a clockwise moment acting. Now this is opposite to the applied virtual rotation, And at point E, the virtual rotation will be same as that of point A because this is a straight line. Okay. Then we go at point F, where there will be an upward delta F, and then we will reach point D, where there will be a downward delta D. So theta E is equal to theta A, delta F becomes 1.5 theta A, and delta D becomes 2 times theta A. Okay, this is again considering small displacements, right? So theta A has to be considered to be small, only then this would make sense. So then we can write the principle of virtual work. So plus ma times theta A minus 20 times theta E minus 30 times delta F plus 20 times delta D. Okay, all of that is equal to 0. So eventually we can solve and we can get ma is equal to 25 kilonewton meter. Always remember to put the units with every numerical expression which has units. Okay, now we can talk about finding VA. So again, now this end A will be converted to a guided roller, and then this is displaced upwards by delta A, right? So again, now respecting the rigidity of the beam and the internal hinge and the supports, so this is the admissible shape which comes out because of this applied delta A. So again, you can see, you can figure out that now there is no rotation at point E because it remains at 0 slope. So theta E is 0, delta F comes out to delta A by 2, and delta D comes out to 2 delta A by 3. And again, writing the principle of virtual work, you can get VA is equal to 5 by 3 kilonewtons. There can be one more approach to finding VA. So given that we have already found MA, okay, so which means that we were considering a beam which had a hinge support at the left end. Instead of going back to the original beam, we can convert this to, let's say, a vertical roller type support. Okay, and then we move it upwards. So now it is able to rotate as well as move up, right? Now if we move up again by delta A at the location A, where VA has been revealed, so if we just move this up by delta A, notice that only this portion will have a non-zero deformation, whereas the rest of it will remain straight as earlier. Okay, so which means that now, but of course, the other thing is that in the previous case, this span remained straight, whereas now this span has become inclined. Okay, so there will be work done by MA also. Okay, so theta A becomes delta A by 3 in the clockwise direction, which is also equal to theta E, and delta F and delta D remain 0. Okay, so the expression may become a little simpler. So we are just writing now VA times delta A minus 25, this is MA, minus 25 times delta A by 3 plus 20 times delta A by 3. This 20 is this clockwise moment. Okay, so again, solving this, we can get VA is equal to 5 by 3 kilonewtons. Now for finding out VC, we will release, so this was a roller support, this will become totally free, and we will apply a virtual displacement here. Let's say it is delta C, right? Now B is a hinge, and this will be a straight line. From B to D it will be a straight line. So after application of this delta C, there are two induced displacements. One is delta F and one is delta D, and we can find out that delta F is delta C by 2 and delta D is 5 by 3 delta C. And again, you can apply principle of virtual work, and you can verify that the VC comes out to be 145 by 3 kilonewtons. Let's look at an example of a frame. So let's say this again simply supported sort of frame is given, where the column is of height 3 meters and beam is of length 4 meters, and there is a force of 50 kilonewton being applied, and we have to find support reaction at A. So this hinge we convert to a vertical roller. So we release movement in the vertical direction. So this will reveal the force VA, or the support reaction VA. Okay, and then we give an upward delta A at the point A. Uh, Now remember that this delta A will be very small. So if the point A moves upward by delta A, this point B also moves upwards by the same amount delta A. And because of this movement, since this 50 is being applied at the midpoint of BC, the upward movement of the 50 kilonewton application point will be delta A by 2. Okay, so again, then principle of virtual work can be applied, and VA can be found out to be 25 kilonewtons. Next, let us look at application of this principle of virtual displacement in finding internal forces. So up to now we were finding external support reactions, but we can also see how we can find the shear force or bending moment inside a beam. So let's say this is a simply supported beam which is given, and we have to find shear force and bending moment at D. Okay, so at point D we have to find the shear force and bending moment. Now to find the shear force, we cut it at D. Okay, and we displace it so that the portion AD and the portion DB, they have equal slopes. Okay, and you may recall that the sign convention for shear forces and bending moments. So if to the left of a support it is acting upwards, in the right support in the right side it will act downwards, and same thing for M. Right. So when we cut it, the shear force SD gets revealed, and also the internal bending moment MD gets revealed. Okay. Now one is moving up, one is moving down, because we are moving it in the direction of the shear force which we have revealed. And the important constraint here is that the slope of AD and DB are same, which means this theta and this theta are same. Okay, so once we have defined all of this, then we can see that the upward movement at D of the left span is going to be L by 3 times theta, and the downward movement of the right side of the point D is going to be 2L by 3 times theta. Okay, so now we can write the principle of virtual work. So we have plus SD times L by 3 theta plus MD times theta. So this MD times theta is the work done of the left bending moment. Okay, then we have plus SD times 2L by 3 theta. So this is from the right hand side, and then we have minus MD times theta, because here for the right span MD is acting clockwise and the virtual displacement is counterclockwise, and then there is work done by the force, which is P times L by 3 times theta. Right, and solving all of this we get the shear force at point D, which is minus P by 3. Now to find out the bending moment, we can consider an internal hinge at point D. Okay, so once we consider point D to be an internal hinge, only the moments MD will be revealed for the left and the right supports, for the left and the right sides of the point D. Okay, and then we give an upward displacement, let's say delta. Now the key here is that the delta of the left portion and the right portion are the same. Because if this was, you can also imagine that this was again completely cut and not really internal hinge, then the shear force will be acting upwards on the left span and downwards on the right span. And if the displacement is in the same direction and equal for both cases, the virtual work of the shear force will get cancelled out. So just like because the slopes were same in this case, in the earlier case, the work done by the bending moment cancelled out. Okay, similarly, since we have considered single displacement in the same direction, the work done by the shear force will get cancelled out. And now we can again, so once we define this as delta, from geometry we can find out what are the angles at which the left and the right spans have moved. And then we can write the principle of virtual work again. So plus md times 3 delta by L, this is due to bending moment of the left portion, plus md times 3 delta by 2L, this is the work done of the right portion bending moment. Okay, minus p delta by 2, this is the work done due to the applied force, and eventually then we get md equals to pl by 9. So this is how we apply the principle of virtual work for finding support reactions and for finding internal forces in the beams. And later on we will see how to apply principle of virtual work in cases of deformed bodies. So when we consider deformations due to bending or deformations due to shear force inside a beam, so even those can be easily calculated using the principle of virtual work. And this also gives rise to things like the unit displacement method or the unit load method. So all of these we will see in the subsequent sessions.